Hi, my name is Junseong Kim, and I'm from Seoul National University. In this talk, I'll present NLP-Fast, a fast, scalable, and flexible system for large-scale heterogeneous NLP models. This work is done with my co-workers and my advisor, Professor Jang-woo Kim. Recently, neural networks are widely used for various natural language processing applications. For example, speech recognition, machine translation, and question and answering. These neural network-based NLP models have two characteristics. First, the model scalability. To achieve the high reasoning power, the network size has been continuously increasing. Second, the model diversity. As each NLP model is customized for their own purposes, there are huge diversity in recent NLP models. These large-scale heterogeneous NLP models require a fast and scalable system architecture. However, these NLP models suffer from the limited scalability due to the following reasons. First, the increasing network size incurs large memory bandwidth requirement and high computation demands. Also, the various NLP models occur a huge performance variation, which makes the system architect hard to figure out the critical performance bottlenecks. In this work, we will present NLP-Fast to achieve highly scalable computing architecture for large-scale and heterogeneous NLP models. Let me introduce background and motivation of our work. First, I will explain basic computational steps of recent NLP models. Before explaining the computational details, I will briefly introduce the key computations in recent NLP models. First, we classify recent NLP models into three representative models: memory networks from Facebook, Transformer, and BERT from Google. Then, for these NLP models, we identify their key computational components: attention mechanism, multi-head attention, multi-head self-attention, and feed-forward network. I will explain the computational details of each component in the following slides. First, I will illustrate typical operation in the attention mechanism. For a given query and key value pairs, the attention mechanism first computes dot product between a query and keys to calculate score values. Then, it calculates a probability vector by applying the softmax function to the score vector. Next, it computes the weighted sum with the given values to derive the final answer. Here, the attention mechanism consists of three operations: dot product, softmax, and weighted sum. In this slide, I will explain the multi-head attention and multi-head self-attention. The multi-head attention consists of multiple attention mechanisms. It calculates the final output by applying the reduction on each attention result. Also, different from the attention mechanism, the multi-head attention generates query vectors from the input data. Here, the key difference between the multi-head attention and multi-head self-attention is that the multi-head self-attention generates all key and value vectors from the given input data. The last component is a feed-forward network. As shown in the figure, the feed-forward network consists of two linear transformations and one activation function between them. Finally, we can conclude that the NLP models consist of various operations which result in the high model complexity. Next, I will introduce performance problems existed in these large-scale and heterogeneous NLP models. First, the large-scale NLP model incurs a large number of memory requests. The figure shows the example attention mechanism. As the network size increases, the on-chip cache cannot keep this large number of memory requests anymore. Most requests are sent to the off-chip DRAM. Since we have limited DRAM bandwidth, this increasing size of spilled data makes the current system hard to achieve scalable performance. Second performance problem is high computation overhead. As the NLP model consists of various compute-intensive operations, and the network size continuously increases, the NLP models require a large amount of computation. Such huge computation overhead makes the current system difficult to provide scalable performance. The last limitation is the huge performance variation. The figure shows the latency breakdown for various NLP models. X-axis shows the different NLP models with different model configurations. Here, the interesting thing is that there is the huge performance variation between each NLP model and configuration. For example, the attention mechanism dominates the total execution time in memory network. However, it is not major performance bottleneck anymore in transformer and BERT. To summarize, for the large-scale and heterogeneous NLP models, the current system architecture cannot provide scalable performance because of high memory traffic, heavy computation overhead, and huge performance variation. From now on, we propose NLP-Fast to resolve those performance problems to achieve highly scalable and flexible system architecture. Let's move on to our key ideas. We propose 3 effective optimizations. First, NLP-Fast can reduce the off-chip memory traffic by using holistic model partitioning. Second, NLP-Fast applies cross-operation zero-skipping to reduce the amount of computation. Third, NLP model can resolve the performance variation by using the adaptive hardware reconfiguration. Here, our optimizations are widely applicable solutions. Therefore, it can be applied to various hardware platforms, for example, CPU, GPU, and FPGA. First, we propose a holistic model partitioning. The key concept is that it applies the model partition to all aforementioned operations in NLP models. By doing so, we can reduce the working set size, which significantly improves the cache efficiency. Here, we propose 3 techniques: partial head update, column-based algorithm, and feed-forward splitting. Due to time constraints, I will only explain column-based algorithm in this talk. Here is the column-based algorithm to reduce the working set size in the attention mechanism. The left equation shows the original computational algorithm of the attention mechanism. From this equation, a denominator is independent from the summation index I. Therefore, we can pull the denominator out of the summation. By doing so, we can partition the entire data into small chunks, and we can perform the computation on each chunk independently. This fine-grained execution provides 2 benefits. First, now the on-chip cache can handle the intermediate values. Therefore, the number of DRAM accesses is significantly reduced. Second, as the chunk size is reduced, now we can prefetch the next key and value memory blocks to hide DRAM accessing overhead. Here, we propose 2 types of computation skipping optimization: zero skipping and V-gen skipping. First, in the attention mechanism, the zero skipping optimization performs the computations only if the score value is larger than a certain threshold. By doing so, it can successfully reduce a large amount of computations in the attention mechanism. Second, the V-gen skipping optimization skips the unnecessary computations during the value matrix generation. By doing so, it can skip most computations during the value generation process. For each optimization, we adopt certain threshold values. For example, score threshold for zero skipping and zero ratio threshold for V-gen skipping. Here, since we skip the computations, Someone may be concerned about an accuracy loss. Therefore, we measure the trade-off between the skip ratio and the accuracy loss for each threshold value. In the figure, x-axis means the threshold values. Left y-axis and red line show the accuracy loss, and right y-axis and dotted line show the skip ratio. We can observe that it is possible to achieve the high skip ratio with a minimal accuracy loss. For example, when we set the score threshold as 0, we can skip 73.9% operations with 0.23% accuracy loss. We will use this score threshold and skip ratio for the evaluation. As I explained earlier, there is the huge performance variation in recent NLP models. To find the optimal design point for each NLP model and configuration, we proposed adaptive hardware reconfiguration. It consists of 2 steps. First, we allocate the hardware resources to each operation based on the latency profiling results. By doing so, we can statically allocate more resources on the performance-critical operations. Next, we reallocate the hardware resources to minimize the performance gap between memory and computation to find the optimal pipelining structure. With these optimizations, we can find the optimal design point for each NLP model and configuration. To verify the effectiveness of NLP-Fast, we implement NLP-Fast on 3 different hardware platforms: CPU, GPU, and FPGA. Here is the high-level architecture overview of NLP-Fast. Different from the baseline, NLP-Fast adopts 3 key optimizations: holistic model partitioning, cross-operation zero-skipping, and adaptive hardware reconfiguration. As you can see, we first add several reduced sum operations for the holistic model partitioning. For cross-operation zero-skipping, we add simple comparators to check whether the intermediate value is smaller than certain thresholds or not. If the value is smaller than the certain threshold, we skip the remaining computations. Lastly, for reconfigurable hardware, we apply the adaptive hardware reconfiguration to find the optimal design point for a given NLP model and configuration. Now I will explain architecture-specific implementation details. We implemented NLP-Fast on CPU, GPU, and FPGA. First, for CPU implementation, we applied 2 software-based optimizations: holistic model partitioning and cross-operation zero-skipping. Next, for GPU implementation, we only apply holistic model partitioning. Here, zero-skipping optimizations are inefficient for GPU because it requires expensive data compaction before the execution. Lastly, we apply all optimizations for FPGA implementation. Let's move on to the evaluation result of NLP-Fast. First, I will show the scalability of NLP-Fast by using GPU results. Different from the baseline, which requires multiple synchronization between each operation, our NLP-Fast only requires the synchronization at each reduction operation. Therefore, NLP-Fast can successfully reduce the synchronization overhead and achieve scalable performance improvement. Lastly, I will present the performance impact of the adaptive hardware reconfiguration. For this evaluation, we used a BERT model with different parameter configurations. Here, x-axis shows the BERT model with different configurations, and y-axis means the performance speedup compared to the base configuration. As you can see, our adaptive hardware reconfiguration significantly improves the overall performance by finding the optimal design point for each model and configuration. I'd like to conclude by summarizing main points. First, we identified the performance problems existed in large-scale and heterogeneous NLP models. Next, we proposed NLP-Fast, a fast, scalable, and flexible system architecture for recent NLP models. Lastly, we implemented NLP-Fast on various hardware platforms and show its effectiveness. Thank you for your attention, and I'm ready to answer your question.